All right, we're going to start the second part of the lesson in Module 1, Topic 3, Lesson 2. Starting off with Activity 2.3, using the correlation coefficient to assess a line of best fit. Here we have a situation. The amount of antibiotic that remains in your body over a period of time varies from one drug to the next. The table given shows the amount of antibiotic X that remains in your body over a period of 2 days. Determine and interpret a linear regression equation for this data set. So we're going to take our graphing calculator and enter this set of data. Remember, we need to go to Stat and Edit. List 1 is going to be my domain, my input, my independent, 0, 6, and then we need to go over and enter our dependent, our Y values. All right, now that we have those entered, we're going to go back to statistics and we're going to calculate the linear regression, number 4, and keep hitting enter. And here we look at our correlation coefficient. It's a little weak. It's okay. It's not very strong. We're going to start looking at the coefficient of determination, and that is not very close to 1. So we're going to look at that and see why. So number 1, we're going to write the equation of the line of linear regression. So remember, that's in slope-intercept form. Your calculator uses ax plus b. A is your slope, negative 1.07. And we'll actually just round that up to negative 1.1. Really doesn't matter where you round. X plus 42.3. So that will be our linear regression equation. Number 2, it says compute and interpret the correlation coefficient, which is R, and the coefficient of determination, which is R squared. So R is negative 0.8832, and the coefficient of determination is 0.7800. And we're going to take a look at these. Number 3, does it seem appropriate to use a line of best fit? If no, explain your reasoning. So, since our linear regression and coefficient of determination are not extremely close to negative 1 and 1, respectively, indicating that a linear function may not be the best result. So since R and R squared are not close to negative 1 or 1, that is telling me it is not a linear function. So we're going to look closely at the graph to see what it is. Sketch a scatter plot of the data. So here I went ahead and I plotted those points up here from the table on this graph. And you can see how on this data it is showing an exponential function. Remember that an exponential function either decreases greatly or increases, and this one seems to be approaching the x-axis, but it's not going to cross it. So number 5 says, look at the graph of the data. Do you still agree with your answer number 3? Yes, I do agree. I don't think it's a linear function. The data appears to be exponential. The data appears to be exponential. Activity 2.4, correlation versus causation. Does correlation mean causation? What do you think causation means? That is a question that statisticians are always trying to determine. If I were you, I would pause this video and I would Google correlation and causation to get an idea of what they represent. Let's look at these examples. Read the 3 true statements that Alonzo and Richard are given by their Algebra 1 teacher. She asked them to decide what conclusions they can draw from the data. Do you agree with them? If so, why? If not, why not? Number 1, the number of smartphones sold in the United States has increased every year since 2005. The number of flat-screen televisions sold in the United States also has increased during the same period of time. Alonzo and Richard reached the conclusion that owning a cell phone causes a person to buy a flat-screen TV. Let's think about that for a second. This is a true statement. Cell phones have increased. Flat-screen TVs purchases have increased. But are they correlated? Does one cause the other one? That's a causation. There is no evidence that buying a smartphone causes a person to buy a flat-screen TV. Most people buy a flat screen because that's the only type available. Also, all technology sales are increasing in this day and time. So let's look at number 2. Since 2004, the average salary of an NFL football player has increased every year. The average weight of an NFL football player also increased yearly since 2004. So, true statements. After much discussion, Alonzo and Richard reached the conclusion that higher salaries cause the players to gain weight. Well, I think we know that it doesn't. However, these are true statements. One does not cause the other. The increase in pay does not cause a player to gain weight. However, it could be argued that increasing pay has given an incentive to players to become bigger and stronger. Let's look at number 3. Worldwide, the number of automobiles sold annually has steadily increased since 1920. Gasoline production has also steadily increased since 1920. Both true statements. Alonzo and Richard conclude that the increase in the number of automobiles sold caused an increase in the amount of gasoline produced. It does seem reasonable that the increase in the number of automobiles has caused an increase in the amount of gasoline production. Proving causation is challenging. The scenarios Alonzo and Richard analyzed demonstrate that even though two quantities are correlated, this does not mean that one quantity caused the other. This is one of the most misunderstood and misapplied uses of statistics. Causation, grab your highlighter, kids, is when one event affects the outcome of a second event. A correlation is a necessary condition for causation, but a correlation is not a significant condition for causation. While determining a correlation is straightforward, using statistics to establish causation is very difficult. Let's take a look. Many medical studies have tried to prove that smoking causes lung cancer. Part A. Is smoking a necessary condition for lung cancer? Why or why not? So I'm going to underline the word necessary condition. Is smoking a necessary condition for lung cancer? Think about that. Well, no. People can have lung cancer without ever smoking. So no. Part B. Is smoking a significant condition for lung cancer? Why or why not? No, not every person who smokes gets lung cancer. Part C. Is there a correlation between people who smoke and people who get lung cancer? Yes, smokers have much higher incidence of lung cancer than non-smokers. So there is a correlation. Part D. Is it true that smoking causes lung cancer? If so, how is it proven? Yes, scientists have proven that smoking causes lung cancer by first finding a high correlation between smokers and lung cancer, and then by discovering that smoking damages lung tissue, which encourages the development of the lung cancer. So yes. Number 5, it is often said that teenage drivers cause automobile accidents. Part A, is being a teenage driver a necessary condition to have an automobile accident? No, drivers other than teenagers have had accidents. Part B, is being a teenage driver a significant condition to have an automobile accident? No, not all teenage drivers have accidents. Part C, is there a correlation between teenage drivers and automobile accidents? Yes, teenage drivers have a higher accident rate than other drivers. Part D, is it true that teenage drivers cause automobile accidents? Explain your reasoning. Yes, teenage drivers do have more accidents, which can be caused by a number of related factors, including they have less experience, they're more distracted, and so on. Here's another example. Does school absenteeism cause poor performance in school? A correlation between the independent variable of days missed to the dependent variable of grades makes sense. However, this alone does not prove causation. Remember, causation is something that causes the other effect. Number 6, in order to prove the number of days that a student is absent causes the student to get poor grades, we would need to conduct more controlled experiments. Part A, list several ways that you could design experiments to attempt to prove this assertion. Well, I could have the same students go to school every day for a semester and stay home 20 days for the next semester. Then compare their grades from one semester to the next. I could find 2 students with similar grades and have one stay home more than the other, and then compare their grades after a period of time. I could examine the total number of days absent and the grades of a much larger number of students. Keep in mind, these questions were designed before our lovely remote learning. So even though we are still learning online, you have to think back to when we were not learning online and how getting those lessons were a little bit more difficult. Part B. Will any of these experiments prove the assertion? Well, yeah, it could help. Some of them, no. It just depends on what experiments that you do. There are two relationships that are often mistaken for causation. A common response is when some other reason may cause the same result. A confounding variable is when the other variable that are unknown or unobserved. Number 7, consider each relationship. List 2 or more common responses that could also cause the result. In North Carolina, the number of shark attacks increased when the temperature increased. Therefore, a temperature increase appears to cause shark attacks. Well, I love going to the beach, but the higher temperatures do not cause more shark attacks. Think about what's going to cause the shark attacks. When the temperature goes up, there's going to be more people swimming, and that's going to increase the activity for the sharks. Therefore, that's going to increase the shark attack, not necessarily the temperature. Part B. A company claims that their weight loss pill caused people to lose 20 pounds when following the company exercise program. Well, maybe it was just the exercising that caused them to lose the weight. Maybe they were eating better. Maybe they were given a placebo pill and not an actual diet pill. So even though they were losing weight, it may not be from that magical weight loss pill. Talk the talk. Correlations are us. Consider the given data sets. Determine the linear regression for each set. So we're going to take our graphing calculator, type in those values. I'll do set A, you can do set B. Go to statistics, edit. What we can do, and I'll show you this trick real quick, is we can go back to stat and we can clear our set out. So hit clear list, and I want to clear list L1, so I'm going to hit second and 1. Done. And if you go under statistics, you will see that list 1 is cleared out. Then I can clear out list 2, 4, second, 2 gives me clear list L2, hit done, go back to statistics, edit, and they're all cleared out. So I'm going to hit my X values, 0, enter 2, and then go over to my Y's. And calculate. I did that again, I don't think. Let's see, I need L1 in there. There we go. So what do you notice here? Negative 0.95, that is a good, strong, negative correlation. I've got 0.9 here for my correlation determination. So this tells me it's linear. This tells me it is a strong correlation. Determine the regression for each set. So here, my regression will be y equals negative 1.1 x plus 20.7. I would definitely say that this was linear. Number 2, compare the correlation coefficient and the coefficient of determination for each data set. Describe which regression equation is better fit and why. So let's see, kind of just draw a line through the middle. I'm going to put this equation over here, negative 1.1x plus 20.7, and we'll do set B over here. And let's see, I've got my R is negative 0.9512. My R squared, which is my coefficient of determination, is 0.9048. And then I'll come over here and enter set B. I think I'll just put my numbers on top there. And I'll do 8. Here we go. Ooh, interesting numbers here. So my correlation coefficient is not good. This tells me that it probably is not linear, and then I definitely is confirmed that this is not linear. That needs to be closer to 1 to determine that it's a linear function. So let's write that information down. If this was linear, I would write it, well, the line of regression is linear. Let me make that clear. This data is not linear. So let me see if I can give you an example of that. So this would be 5.08x minus 43.3. That is the linear regression line. Okay, it's trying to go through the center of the data, and I'll show you what that looks like on the calculator. But according to these calculations, we don't have a strong correlation, and based on the coefficient of determination, it is not linear. So let's turn my plot on. So my plot on is above the Y. So I hit second plot. So I've already got L1 and L2 turned on. You may have to turn yours on just by hitting enter. All my other lists are turned off. Let's see. I don't have any other lines plugged in there, and it says that my plot 1 is on. You can see it darkened in there. I'm going to type in, I'm just looking at set B right now. I'm going to type in this line of best fit, this linear regression. So 5.08x minus 43.3. So it's going to graph the points, and it's going to graph this line now. Hit graph. And my window's a little off, so I need to zoom in. And I'm going to hit, if you go to zoom and hit 6, it'll give you your standard 10 by 10 window. So there's my line of regression, and you can see one of the points there. So let's see, I need to move over to maybe to the right because I've got 19 and 73 that I need to look at. I can use my arrows, see my cursor pop up, And I can just hit zoom in and hit enter again. Maybe I can see some more data points. And I don't. I need to move up. Zoom. Maybe just zoom out. You can keep playing with this. There's one data point. So I'm going to go up a little bit more. Over. Zoom out. There's some more data points, and there is my linear regression. Let's see if I can zoom in to that area. So I've got 4 points that you can see, and 3 points are on one side and 1 point's on the other. So let's see, 19 and 73. So let's say zoom out. And I'm going to zoom out again. So those are all the points that I can see. That other one's still up there. Well, I had a better picture earlier. Now I've got a good picture of my data. What I did was I hit zoom and I went down and I saw zoom statistics. So that put it all on one screen for me. So you can see here that it's not linear. You may even want to think maybe it's quadratic in this situation, but definitely not linear. And that's what the correlation coefficient and the coefficient of determination help us to discover. So, data set A, definitely linear. We had a strong correlation coefficient. Data set B, the R value is closer to 1. Also, set A's R square value is higher percentage than set B's R value. So this one's linear. This one we're not quite sure, but definitely not linear. This is a better representation.